we finished the day by showing that a product of 4 reflections is necessarily a product of 2 reflections. Okay, and I stated the following theorem, which we'll finish the proof of today. First, have an even isometry is a product of 2 reflections and odd isometry is a reflection or a product of 3 reflections and furthermore, the main thing we wanted to prove, no isometry is both even and odd. Okay? So hopefully you'll remember that this was our main goal in showing that even and odd is a useful concept for isometries, so that we can further classify the different types of isometries and say what properties they have. That's what we are aiming to use even and odd for. Okay, so here's the proof. So repeated application of yesterday's theorem, that is, a product of 4 reflections can be expressed as a product of 2 reflections always, shows any even isometry is a product of 2 reflections. Right? Say I have a product of 6 reflections. Well, I can take any adjacent 4 reflections and express them as 2 reflections. And then I have a product of 4 reflections, so I can reduce it to a product of 2 reflections. Okay, so I'm not going to do the formal induction necessary to prove this in full formality, but I think the idea is clear, right? If you have any even number of reflections, right, that's what it means for an isometry to be even, that it's expressed as an even number of reflections, right? A product of an even number of reflections. We can take any consecutive 4 and reduce it to 2, and then do that again and again until we get down to just 2 reflections. And I'll just say, likewise, for odd isometries. That is, it's the same type of inductive argument, but there's 2 possible outcomes. You either have 1 reflection at the end or a product of 3 reflections. The same procedure, just take any 4 adjacent reflections and turn it into 2. And repeat that process until you either get to 1 reflection left or 3 reflections. To show an odd isometry is a single reflection or a product of 3 reflections. Okay, so straightforward. So straightforward that I'm actually not giving you the full formal argument, the induction. Now, we still have to address this last part of the theorem that no isometry is both even and odd, which is the most important thing that we wanted to know. So, to finish the proof, we must show, what must we show? We have to show that a product of 2 reflections cannot be expressed as a single reflection, nor a product of 3 reflections. Okay? We must show a product of 2 reflections cannot be written as a reflection or a product of 3. Okay, so we'll proceed by contradiction. All right, so let's assume that we have 5 lines. Assume we have 5 lines, P, Q, R, S, and T, such that we have the following. We have sigma R, sigma S, sigma T is equal to, oh, sorry, just want to make my notation consistent with my notes. So this is actually P and Q is equal to sigma S, sigma T. Okay, so we'll assume that a product of 2 reflections can be written as a product of 3 reflections. That there are some lines, P, Q, R, S, and T, that satisfy this equation. Okay, well, of course, this implies that if we just multiply by sigma T, sigma S on the left, both sides, we get sigma S, sigma R, sigma P, sigma Q is equal to sigma T. Okay? Now, what do we have here? Product of 4 reflections. So by our main theorem from last time, we know there are lines L and M, so that sigma M sigma L is equal to this product of 4 Okay? So I should make a note here. Where we started is one of the two cases that we need to verify can't happen, right? So now, starting with the case of trying to express the product of two reflections as the product of three reflections, we now get to a place where we have to address the case of expressing the product of two reflections as one reflection. Okay? So in other words, once we verify the case that two reflections cannot be expressed as one reflection, then we will have necessarily shown this case that we started with can't happen. Okay? Okay, now, however, we spent the last couple days showing that the product of two reflections is either a translation or a rotation, right? The product of two reflections must be a translation or rotation. And just a side note here, what does that depend on? If I take the product of two reflections, how do I know whether it's a translation or a rotation? Well, that depends on whether the lines M and L are parallel or intersect somewhere, right? That's what we spent the bulk of Wednesday and Thursday talking about. Okay, so now a translation has no fixed points, a non-identity translation has no fixed points, and a non-identity rotation has exactly one fixed point. Whereas a single reflection has the entire line T are all fixed points. So neither case allows the product of two reflections to be a single reflection. Okay? So, now there's no doubt that the notion of even and odd, as we define it for isometries, is a well-defined concept. It's useful to us because no isometry can be both even and odd. Okay? So here's a corollary. And even involuntary isometry is a half term. And odd involuntary isometry is a reflection. Okay. Why is this? Well, we already classified all the involuntary isometries, right? We already proved that they're half-turns and reflections. Okay? Now a reflection is obviously just a single reflection, so it must be odd. Okay? And a half-turn is a type of rotation, right? It's a rotation by 180 degrees. So, we know, being a rotation, it can be expressed as the product of two reflections. Namely, because it's a rotation by 180 degrees, it has to be expressed as a product of reflections in two perpendicular lines. Okay? So, this corollary just follows from the theorem that we just proved and the fact that we classified all the involuntary isometries and know that they're only half-turns and reflections. Furthermore, we know the structure of half-turns and reflections. All right? So, here's the first useful thing that we can say about either even or odd isometries. The set of even isometries which we denote script E forms a group. Okay, so there's one slightly confusing thing about this. Namely, that even though when we do arithmetic, technically 0 is not even or odd, right? But in the context of isometries, we count 0 as even, right? So that is to say, in other words, iota, the identity, is a product of 0 reflections. Or, if you like, you could just as well, there's no need to make this convention. Or, you could just say iota is equal to sigma L for any line L. Okay? So, iota is even. So in other words, script E has the identity property, right? Okay. So, now, what if we take a product of reflections, let's say reflection in line L1 times reflection in line L2 times reflection in line L3, all the way up to reflection in line 2n. We take the inverse of this, okay? So I have lines L1 through L2n, some even number. Okay, so I'm taking the inverse of an even isometry. The thing inside this inverse is even, right? Well, we know how to take the inverse of any product of isometries. It's just, we flip the order and take the inverse of each element, right? So we get sigma L to N inverse, sigma L3 inverse, sigma L2 inverse, down to sigma L1 inverse. Well, what does this mean? This means that the inverse of any even isometry is also even. So the inverse of any even isometry is even. Okay, good. Script E has the inverse property. All right, now what about closure? Well, E satisfies closure, since if you multiply two even isometries, the result is the product of all isometries appearing in both factors. So, in other words, the product the product of the two isometries we start with will be the product of however many reflections the first isometry was a product of, plus however many isometries the second reflection was a product of, right? So we're just adding two even numbers, which gives us an even number. Now, there's one subtlety I'm glossing over here. Any thoughts on that? Well, what if, let's just take a really simple example. Let's say I have isometry alpha equal to sigma sub L, sigma sub M, and beta equal to sigma sub N, sigma sub L. And then I take the product, beta alpha is equal to, well, I should give myself a little more space here. Then beta alpha is sigma N, sigma L, sigma L, sigma M. Now, of course, since the reflection is involutive, I drop the sigma L, sigma L, right? So I end up with sigma N, sigma M. Okay? So in other words, I had some cancellation here when I multiplied together these two arbitrary even isometries, but the only way you have cancellation is if you take out two terms at a time. So you'll still be even, okay? So in other words, I have an even number of factors of reflections here, and I have an even number of reflections here. I add them together, I multiply them all together, and I add the total number, I get 4. But then I might get cancellations, right? It might happen that I get the middle terms cancel. But I'm still even because I have an even number, and then I'll take away pairs at most. So I'm still even. Okay? Of course, any collection of transformations is associative. So is script E. Now, so let me ask you, the even isometries form a group. Can we say any similar result for the set of odd isometries? Well, remember, we showed that no isometry can be both odd and even. And here we gave some justification that the identity is even. Therefore, the collection of odd isometries cannot have the identity in it. So I'll just say that. Note, the set of odd isometries does not form a group since the identity iota is even. And what if I take two odd isometries that are just reflections and multiply them together? Well, I get something that's, yeah, right. Thank you, Ian. Odd plus odd can be even, right? And so it's not closed, the set of odd isometries. And odd plus odd is even. Okay? Good. So, in time, we'll see some importance as to why we might want to study the group of even isometries in particular. Okay? For now, just note the group structure. Okay. So now what I want to do is provide some geometric justification for a really common and useful operation in group theory. Okay? So I guess I should say, in general group theory, given a group G and elements alpha and beta in G, we say the element formed by alpha, beta, alpha inverse is beta conjugated by alpha. Okay? So when you study general group theory, this operation of conjugation is an essential part of your study of the structure of a group, its subgroups, its commutativity, what properties it satisfies. So now we're going to take this general notion and provide some geometric intuition for what conjugation means in the group of isometries. Okay? So here's the theorem. If P is a point, little m is a line, and alpha is any isometry then we have a couple of algebraic identities. Alpha times sigma sub m times alpha inverse is just equal to sigma sub alpha of m and entirely similar for the half turn around P. Alpha times sigma sub P, sorry, it's a capital P, times alpha inverse is just equal to sigma sub alpha of P. Okay? Now, this is a little bit heavy on notation, right? So remember, M is a line, meaning that sigma sub M is a reflection. Sigma sub alpha of M is the reflection about the image of the line M under alpha. That is to say, alpha of M is a line as well. Okay, caution here as well. Sigma sub P is a half term because P is a point. Okay, and sigma sub alpha of P is the half turn about the image of P under alpha. Okay? So, let's prove this. First, notice that for any isometries, alpha and beta, alpha, beta, alpha inverse is an involution if and only if beta is an involution. Okay, so why is that? Well, let's just start computing. That is to say, if we want to consider alpha, beta, alpha inverse squared, written out in full form, that just gives us alpha, beta, inverse, alpha, beta, alpha inverse. Okay, so alpha inverse alpha is just iota. So we get alpha beta squared alpha inverse. And if we want this to equal iota, well, then what do we have to do? This is only the case when beta squared is equal to iota, right? In that case, this just becomes iota, and we get alpha times alpha inverse, which is iota. Okay? Okay. So, also note, that alpha beta alpha inverse, the conjugate of beta by alpha, has the same parity as beta. Right? And why is that? Well, it's because alpha and alpha inverse have the same parity. Right? So that means that when we consider beta conjugated by alpha, if the parity of alpha was even, then the parity of alpha and alpha prime, alpha inverse, will contribute two evens, which will give us an even. Okay? If the parity of alpha was odd, then the parity of alpha and the parity of alpha prime contribute two odds, so we get an even. Okay, so no matter what, the number of reflections we're counting from alpha and alpha inverse combined is even. Okay? So now, if beta is even, then we get an even number of reflections from beta plus the even number of reflections from alpha and alpha inverse, which gives us an even parity for alpha beta alpha inverse. Okay? If the parity of beta is odd, then we get an odd number of reflections from beta and an even number of reflections from alpha and alpha inverse. So adding an even to an odd gives you an odd, which is the same parity as that of beta. Okay? So, now we want to consider the two types of involutions that we know characterize all involutions: reflections and half-turns. Okay, so let's start with half-turns. So, given a half-turn, sigma sub p, which we know is even, which must be even. We know alpha sigma sub p alpha inverse is an even involution, right? Because sigma sub p is an involution, which is even. So by the first two notes we made, we know that alpha sigma sub p alpha inverse must be an even involution, which implies alpha sigma sub p alpha inverse is a half-turn. point. So what point does this half turn fix? Any thought there? Well, let's see what happens if we put in alpha of p. Let's compute. So we want to take alpha times sigma sub p times alpha inverse of alpha of p. Okay, so alpha inverse of alpha of p is just p, right? So I get alpha times sigma sub p of p. P is the point that sigma sub p fixes, so this just gives me alpha of p, which is what I started with, which is what I put in to the half turn in the first place. So, in other words, I can write alpha sigma sub p alpha inverse as sigma sub alpha of p, right? That is to say, the half turn that fixes alpha sub p. Okay? All right, so entirely similarly, we know that sigma sub m is odd, being a single reflection, right? So this implies alpha sigma sub m, alpha inverse is an odd involution that fixes the line alpha of m. Okay, we'll quickly run through the computation again. Now, of course, the symbols look exactly the same, but now we're dealing with a set, right? Alpha of m is the image line of m. Okay, so alpha inverse of alpha of m is just m, so we get alpha of sigma sub m of m. Sigma sub m fixes the line m, so we just end up with alpha of m again. Okay? All right. So let's do an example of this, a highly visual example. Okay, so let's see. Okay, yeah. We need a lot of space on the board, so you just get ready. Let's let alpha be, so alphas are arbitrary isometry that we're going to conjugate by. So let's choose alpha to be the rotation centered at P, which rotates by 60 degrees. M, some line not containing P. And the reason I say that is just because it's going to be easier to see what's going on if we take P off the line M. Okay? So here's what I'm going to do. Here's what we want to do. Let's draw what conjugation means. What the conjugation alpha sigma sub m alpha inverse means. Okay, so step one. I guess I'll write it down. Step one. We'll take alpha inverse, which of course is just rho sub p comma 60. What's the inverse of a rotation? Well, we just slap a negative sign on the angle we're rotating by, right? Rho sub p comma negative 60. Okay, now here's my schematic diagram. Here's a point P, and here's a line M. And just to see, just as an indicator of what operations I'm doing, I'll use this letter F here. Why do I choose the letter F? Just because it's pretty asymmetric, right? So when I do an operation on it, it'll be kind of easier to see what happened. Okay? So step one, I'm going to do this isometry. So I'm going to move everything over negative 60 degrees, right? And I really wanted a colored marker for this, but unfortunately I don't have any. Okay? So if I rotate this F negative 60 degrees, I get something like this, right? So I guess I'll say 1 and 2. This is before the rotation by negative 60, and this is after the rotation by negative 60. Okay? So, step 2. We'll do sigma sub m. Okay? So, still have my point P and my line M. And I have my F shape here. And when I reflect it about M, what do I get? I get this, right? Okay? So now, step 3. I will do just the standard rotation, rho sub p comma 60. And so let me redraw my diagram again. I have P, have my line M, and now my F is here. I'll put a 1 there to indicate. Then I rotate 60 degrees around P. And what do I get? I get this F, right? So these three steps are the same as applying sigma sub rho sub p comma 60 of m. Okay, so this is a little confusing the first time you see it, right? Sigma is the normal size font, and then rho is a subscript, and then p comma 60 is a subscript on the subscript, right? This is, remember I set this equal to alpha. So we have to look at the image of our line M under alpha. Okay? So, one final diagram. Here's our point P. Again, we have our point M. Now, what is the image of M under rotation by 60 around P? Right? I take M and I rotate it by 60 degrees. And we'll call this N, or this somewhat more cumbersome notation, rho sub P comma 60 of M. So now I start with my same F1 back from step 1. And what do? I operate the reflection about N. That is rho sub P comma 60 of M. And what do I get? The same thing that I got from doing steps 1, 2, and 3 in order. I've done a single geometric step. Okay? That kind of illustrates the power of this notion of conjugation and the algebraic rules we derive from that. Okay? So, let us continue. I hope that this labeling scheme is clear. I know there's a lot of subscripts flying around. Okay? Okay. So, all right, so we know how to conjugate any involuntary isometry, right? And we come up with a very nice formula. So now, let's see what we can say about conjugating the other two main types of isometries that we have discussed at great length so far. Okay? That is to say, let us describe what happens when we conjugate a translation or a rotation by an arbitrary isometry. All right? So, again, let's say alpha is an isometry, any isometry. Then we have alpha times tau sub a comma b. Alpha inverse is just equal to tau sub alpha of A comma alpha of B, and also alpha times rho sub C comma theta, an arbitrary rotation, alpha inverse, is equal to rho sub alpha of C comma plus or minus theta. Now where does this plus or minus come from? Well, I'll tell you where theta is positive if alpha is an even isometry and theta is negative if alpha is an odd isometry. Okay. So let's see here. So the case of a translation is not all that hard. And the case of rotation takes a little bit more work. So let's address translation first. Okay? So for translation, tau sub A comma B, let's let M be the midpoint of the line segment AB. Okay? Which, of course, since alpha is an isometry, means alpha M is the midpoint of alpha A, alpha B. Yeah? So then recall, we can write a translation as a product of half terms, right? Once we know the midpoint, we can write it very simply as, for example, tau sub A comma B is equal to sigma M, sigma A, right? And likewise, we have the same thing in the image of alpha. Tau sub alpha A comma alpha B is equal to sigma sub alpha M, sigma sub alpha A. Okay? So, now let's compute. Compute alpha tau sub A comma B, alpha inverse. Well, first, we'll just express this as the product of two half terms. Alpha sigma sub M, sigma sub A, alpha inverse. Now, we'll use the same trick that we used a couple times yesterday and insert a copy of iota in between sigma M and sigma A. Okay? So alpha, sigma M, iota, sigma A, alpha inverse. Now, where should I go from here? How do I want to factor iota? Well, I'm dealing with conjugation, and I want to split this into a product of two conjugations, specifically two conjugations that I already know how to deal with. Remember, our first theorem about conjugation was how to conjugate a half term. So I'm going to factor iota as alpha inverse alpha, which gives me alpha sigma M, alpha inverse, alpha sigma A, alpha inverse. Right? So now I have two conjugations that I know how to deal with. Right? So what's sigma sub M conjugated by alpha? Well, that's just sigma sub alpha of M. Likewise here, for sigma sub A conjugated by alpha, we just have sigma sub alpha of A. That's just our second equation up here. Okay? We get tau sub alpha A, comma, alpha B. Okay, so yet another example of that, the usefulness of that trick of inserting a copy of the identity and factoring it the right way that you want to, so that it's useful for you. Okay? So let's finish up on rotations, and I think maybe that'll be it for the day. Okay, so let's say for rotation, rho sub c comma theta, we'll consider three cases. Alpha is a product of 1, 2, or 3 reflections. This is going back to the fact that we proved over a week ago that an arbitrary isometry is the product of at most 3 reflections. Okay, so 1. Let's let alpha equal to sigma sub L for some line L. Then let's let M be the line through C perpendicular to L. So what we know then there is a line N through C such that rho sub c comma theta is equal to sigma n sigma m, right? That would be the line through C. N is the line through C that has directed angle measure theta over 2 from M. Okay? So this is one of the characterizations of how to express a rotation as a product of two reflections that we gave yesterday. Right? I've picked some arbitrary line M through C. That means I know I can find a line. There is a unique line such that, a unique line N, such that I can write this. Right? You don't remember that? Look back in your notes from yesterday. Okay. Such as in the following picture. Okay, so let me just draw a quick picture, show you what's going on. Okay, so we have some line L, and we chose M to be perpendicular to L through the point C, right? And what I'm saying is there is some line N such that the directed angle measure from M to N is theta over 2. Okay. So, notice, then we must have sigma sub L of M is equal to M, right? Because M is perpendicular to L, and reflections fix lines that are perpendicular to the line the reflection is in, right? So, in other words, M is equal to sigma sub L of M. Okay? So, furthermore, and sigma sub L of N intersects M at sigma sub L of C. So let me add this to our diagram. C is here. When I reflect it over L, it comes here, right? Or approximately here. Sigma sub L of C. When I reflect this line N about L, I get this line. Right? This line is sigma sub L of N. Okay? And here, of course, we get the negative of the angle direction, right? If I just flip everything, this arrow is still going from M to N. But now the angle is being traversed in the negative direction, the clockwise direction. So the sign on theta switches. That's where this negative sign comes from. Okay? So, then let's compute. I'll come over here to compute. So we're conjugating like alpha, which remember I just said was sigma L. So we get sigma L of rho sub C comma theta, sigma L. Now, of course, I should say sigma L inverse here, but of course, sigma L is an involution, so I'm just going to leave it that way. Okay? So now I've expressed rho as a product of reflections. So I get sigma L, sigma N, sigma M, sigma L. And now I'll use the same trick. I will insert a copy of the identity and express it as sigma L times sigma L, or if you like, sigma L times sigma L inverse. Sigma L, sigma L, sigma M, sigma L. Okay? So now we're conjugating reflections, which is something we already know how to do. Right? So what does this give us? This gives us sigma sub sigma L of N times sigma sub sigma L of M. Okay? Which is equal to rho sub sigma sub L of C, comma, negative theta. Again, there's no way from just computing you can see the negative sign. And that's because we don't know an explicit analytic formula for rotations yet. We'll get to that in chapter 9. But the geometric picture makes it clear that the sign on the angle switches. Okay? Okay. So just two more cases really quickly. I guess, another way to say this is a motivation for developing analytic geometry is that, when you're working synthetically, you can get to these algebraic calculations, but you necessarily, it's really helpful to actually draw pictures, right? Which is great. I love that aspect of it. But when you start wanting to do things in a computationally efficient way, or even by computer, then analytic things become much more valuable, right? So just a kind of historical note / opinion there. But in any case, let's go on to case 2, where alpha is the product of two reflections, sigma sub t and sigma sub s. Well, now having this pictorial motivation and having to use this, we can proceed just by the algebra. Then alpha rho sub c comma theta alpha inverse is sigma t sigma s rho sub c comma theta sigma t sigma s inverse. Okay, I'm just being extremely explicit here. So this is equal to sigma t sigma s rho sub c comma theta. What do? When I take the inverse of a product, I take the product of the inverses in reverse order. So now I have a conjugate of a conjugate. Okay, and we just did the case when we conjugate by a single reflection, right? So we know that this is just equal to sigma t times rho sub sigma s of c, comma, negative theta, sigma t inverse. And now we just apply the same rule, right? We get rho sub sigma t, sigma s of c, negative theta, which is just theta. We get rho sub alpha of c, comma, theta. Okay? So, and finally, the third case, I'm sure you could guess. Similar calculation shows that we get what we expect. Alpha rho c comma theta alpha inverse is equal to rho sub alpha of c negative theta. Okay, great. So, yeah, this business of conjugation will make your lives a lot easier in computing certain things. And we'll finish chapter 7 on Monday. And, oh yeah, please don't forget to fill out the survey for when everybody would like to go over homework on Tuesday evening. Okay? So have a good weekend, and I'll see you all on Monday. Yep.